Okay, I think let's get started, everyone. Okay, so I just wanted to start off with, there's a big thing that happened in the US this morning, which is that Roe v. Wade was overturned. So this is the law that allows states to like decide whether or not to allow abortion to be legal. And I don't really have anything like intelligent to say about this. I just wanted to say that like I'm thinking about this today, and it's okay if you are too. It's okay if you're not fully present today. You know, it's, I don't know, it sucks, and yeah. So we're gonna keep going, and I hope that if you feel like you need something to sort of distract yourself today, and you want to sort of, you know, be here and be enthusiastic about coding, that this is a way to distract yourself. But it's okay if you need time too. And yeah, let me know if you want to talk about it too. But yeah, I'm going to sort of push forward with the idea of distracting. Okay, on a sort of similar related note, I wanted to plug the anonymous feedback form. We've actually been receiving a lot less anonymous feedback this year than last year. I'm not actually really sure why that is, but yeah, you obviously don't feel pressure to do this, but it is very helpful to us. We are able to, like, you know, change the workshop as it's going based on the anonymous feedback we get. So yeah, definitely encourage you to fill it out as much as you can. And then once more, I think this is the last time this week you'll see this slide. I want to remind you about all the different ways you can ask questions during the workshop. You can ask questions in the chat box. Today I'm going to use Piazza, like lots of responses on Piazza, similar to what Jason's done earlier in the week. You can also ask questions on Piazza. There's an anonymous option. You can ask questions on Discord, and this is the best way to communicate with fellow participants. We're going to be monitoring all of these. So yeah, please ask questions. All of the questions so far of the workshop have been really, really great, and I think have helped people like understand the material more deeply. And then one more reminder about how to group work. We, especially at this point in the workshop, want to remind you that it's okay if you don't want to jump in right away and start working with people. Totally fine to take the first 10 to 15 minutes just thinking on your own. We're going to have an activity today that sort of builds that in explicitly and has time for you to work just by yourself, and then talk to other people. Another best practice is to assign roles and switch your roles often. So here's an example of one of this, is that the driver could be the first person who has the farthest away birthday, the navigator has the closest birthday, and the reporter has the middleest birthday. Yeah.
And that's just not how to do it, so it's like hard to get used to, and I don't really like it, but I was just wondering where it comes from. It's like if there's like research to support that this is like the best way to.
Yeah, sure.
This is from your personal experience.
Yeah, that's a good question. So the question is, where does this the like distribution of roles come from?
Yeah.
Yeah. So I originally got the idea for this came from a pedagogy class that I took at Caltech. I don't know the specific like studies that it was. I can look that up and get back to you. Yeah, but yeah, obviously if you don't like it, or if it doesn't work for you, that's completely fine too. Feel free to do whatever works best for you. This is everything we're doing is sort of just like a suggestion in any way too. Yeah.
Yeah, I was just wondering, it's like sometimes, you know, like the first classes or something, they're like supposed to be like the best way to learn, but sometimes it's like hard to get used to a different way to learn. So I don't know if there was other support for like this being the best way to work it.
Yeah, definitely. Let me look up some, try to like look at some research, some
Okay. Yeah.
resources, and I'll get back to you. But yeah, it's a good question. Thanks for asking. I want to remind you about the goals for the end of the workshop. So I think at this point, you all are pretty much there with all of these. We've talked a lot about and focused on vocabulary. Want to remind you about the vocabulary document too that you can make suggestions for and refer to. You, as of yesterday, you know how to make something pip installable, develop and make something releasable. And yeah, you've been learning throughout the week how to write code that follows the best practices of software development. All right, so in our last day of content, the goals for today are to, so there's going to be a sort of optional type activity at the end with a demo similar to what we did yesterday, that will allow you to implement parallelized Python code for embarrassingly parallel program problems. You can be able to write tests for your code and avoid discriminatory behavior when coding collaboratively. So this is the last day to work on your project as well. The tasks for today are to add tests to your repo and debug your tests, your code so the tests pass. Have an example or demo of your package, maybe like a tutorial. And yeah, just make sure that another group can install and run your package tomorrow. Again, tomorrow's meeting is tomorrow's lesson is totally optional. If you want to participate in the project swap, just make sure you let your TA know. We're trying to keep track of everyone who's participating so we can make project groups together. So this is what the project show and tell is going to look like. You're going to share your projects with two groups. So you might have you could take 5 minutes at the beginning to sort of explain your project to the other group. You'll try and install and run each other's projects following the documentation in their repos. And also give feedback to each other and reflect on the process. I know from personal experience when, the first time people were trying to install packages that I made, I learned a lot and there was a lot of bugs and things that came up that I didn't expect. So I think it's really good practice to watch people try to install and understand your code. Yeah, question.
Example code, is it, do people typically make that available on Read the Docs?
Yes, the question was, do people typically make example code available on Read the Docs? Yeah, I think there are a couple different ways you could do it. You could put it on Read the Docs. You could also just say somewhere on Read the Docs, there are tutorials at this location. But yeah, generally I think in general, you want your docs to be as self-contained as possible. So you don't want people to have to go to multiple places to find documentation and tutorials and stuff. Yeah, good question. Okay. And one more little pep talk. I know this is a tough point in the workshop and that you all have been working extremely hard, and I'm sure everyone's really tired at this point. And when you're tired and overwhelmed, that's when sort of self-doubt starts to creep in. But don't sell yourself short. You can do this. You can, everything you've learned is really valuable, even if you haven't learned everything that we've tried to fire hose at you. So yeah, be proud of yourself for everything you've done so far, and you belong here. And tomorrow, the other optional activity that we're going to have starting at 9 a.m. is a panel on industry software development. So me and Denise, who you haven't met yet, and Simon, where's Simon? Simon's in the back there. Say hi, Simon. That's fine, sorry. Are going to talk about differences between code in industry and code in academia, and the process of applying for jobs in academia in industry from an academic position. And Jason is, say hi, Jason. And Jason, who also has a lot of experience with this, is going to moderate and also contribute his experience. All right, and last, make sure you have the latest version of the Code Astro repository as always. You can type these commands, and yeah, let's get started. All right, so take a minute to appreciate the meme. Okay, so the bulk of today is going to be about software testing. I just want to make a note ahead of time that I'm going to use Piazza polling in this class. So make sure you open up Piazza on your computer so you're ready to answer. So the goals for this lesson are to explain the difference between end-to-end and unit tests, understand why continuous integration systems aid collaborative development, and write tests based on anticipated use cases of your code, and understand what all those words mean. Okay, so I'm going to start off with some motivation for why write tests. Testing is crucial to a code's accuracy and also flexibility. So if you've ever written code, you've probably also tested that code. We don't just write code for, we write code for practical purposes. We want it to do something. And so in order to see whether it does that, we have to test it. But the difference between like writing code that follows best practices and writing any code is that like excellent developers spend most of their time writing tests. Writing tests also isn't something, it sort of sounds like something that you just have to do and it's annoying and takes time and you'd rather be doing something else. But writing tests actually requires creativity. I think writing tests is actually fun. It's important to try and anticipate and test as many use cases of your software as possible. Testing also ensures that your code maintains the same behavior over time. So if you have a set of tests that are passing for your code now, someone makes a change to your code, you can detect if that change like broke any part of your code in an automated way by just rerunning your set of tests. Generally, it's good to keep adding tests over time. So your corpus of tests just grows and grows and grows. So you're testing more and more use cases of your code over time and making sure that that behavior stays constant. So one of our goals for you today is to get in the habit of writing extensive and thorough tests for your code. Okay, so the first goal is to understand the difference between unit tests and end-to-end tests. So let's first focus on unit tests. Unit tests evaluate the correctness of individual elements of your code. So a unit is just the smallest testable part of any software. Unit tests usually have few inputs and outputs. I'll show you an example on the next slide. So some examples of things to test with unit tests are test that the output is correct for every type of input. So if you could put in, for example, a list or an array or another iterable, make sure you put in each of those and test that the outputs make sense. And it's important to include edge cases. Edge cases mean something that might not be like the typical case, but is still allowable by the code. So an example of an edge case is that if your code operates on integers, make sure you test 0, or -1 is another one. If your code operates on strings, make sure you have non-ASCII strings like pi mensae. One question that I get a lot in this section is, how do I test plotting code in an automated way? Generally, we just suggest that in your unit test that you release with your package, you just test that plotting code doesn't fail. It's hard to sort of test in an automated way that plotting code produces the output you expect. It's still important to do that as a developer, but for automated unit tests, good to just test that it runs through. You also don't need to test on inputs that are not allowed by your documentation. If someone, people can break your code in all sorts of wacky ways, and it's your job to anticipate, but not necessarily test for every one of those particular ways. So as an example, if your doc string says that there's a particular argument called myInt was just an integer, you don't need to test a float. You can assume that your users are going to put in an integer. That's not to say that, you know, if users often put in integers that you can't do other things to sort of steer them in the correct direction. Like maybe you might raise a warning or something or an error if that happens, but you don't need to explicitly test it. Okay, so here's an example of a unit test in Orbitize. So I'm going to sort of break this down for you. The first thing you'll notice is that this unit test starts with test underscore. And that's on purpose. There's a package called PyTest, which I'll introduce to you in a second, that collects and runs all functions that start with test underscore. So test underscore is the thing that communicates to PyTest. This is a unit test, run it when I do the automated testing. So what this unit test does is test the functionality of a convenience function in Orbitize. The convenience function is called radec to set PA. So it's converting from right ascension and declination to separation and position angle. If you don't know what those are basically Cartesian coordinates to polar coordinates. So we start off by defining some sample right ascensions and declinations. And then I define the position angles and separations that are expected as outputs from right ascension radec to set PA. There's two different modes of our function radec to set PA, one where we don't mod by 180 and one where we do. So we're testing both of those. And then I run the function and I then have a bunch of assert statements at the bottom. So I'm asserting that the output of the radec to set PA code is approximately equal to the expected output. So here we're also using this pytest.approx function. This is a really handy thing. So in Python, if you want to test that two numbers are equal, say you're testing that pi equals pi that you expect to, a value of pi that you expect to be output from a calculation. If you just say like assert that this version equals this version, maybe at like machine precision they differ, and so Python will tell you, this test didn't pass. These two numbers aren't exactly equal. So pytest.approx says make sure that these are equal to within this absolute error tolerance, in this case of 1e minus 3. So this is a really helpful thing for scientific packages. Okay, so just to review the overall structure of the test, it starts with test underscore. We've got a little description of the test in the doc string, just like we would for any other method or function. We define some sample inputs, some expected outputs. We run the code, and then we use pytest.approx and assert statements to make sure that this is correct. So if you haven't seen assert statements in Python before, the code will fail if this statement evaluates to false. So if these things are not equal, the code will fail. And that's the output that you want for your unit test. You want the code to not run all the way through if something is wrong. Okay, so now for our first Piazza question. What's an edge case we should test for the radec to set PA function? So take like 3 minutes, think of an edge case and type it in on Piazza. Oh, I didn't post it yet. Sorry. Yeah, I have a, one sec. Okay, should be posted. Let me leave up the question, sorry. I don't know if it's live Q&A. think it's just in day 4. Yeah. Yeah, good question. So the question is, what separation from what? What is separation? So it's generally, I think of it as separation from a central star. So if we're trying to track the position of a planet relative to its star over time, you could think of it as either like Cartesian, like there's an X coordinate and a Y coordinate, or there's a separation and then an angle. So we're converting between those two different representations. Yeah, good question. Mhm. Nice. Okay, take 30 more seconds. All right, let's check out the answers. Okay, awesome. So tests where separation and or position angle should be 0. Awesome. Some RA with 90 degrees deck and some with minus 90 degrees deck. Awesome. Yeah, test that the input arrays are the correct size. Yeah, that's a really good one. Another sort of follow-up to the input arrays are the correct size, like test the empty array, or like test different dimensional arrays if you're, I don't remember if we accept multi-dimensional arrays in this, but if we do, then you should test that. 0, 0, 0 as both test inputs, 0 and 180. Awesome. Stars that are exactly opposite on the sky. Yep, 0, 0, RA or deck equal 90. Yeah, awesome. If RA or deck are lists, yep, RA greater than 360, that's a really good one too. Nice, awesome. All of these are really great examples. Nice job, y'all. All right, so now that you are experts on unit tests, let's go on to end-to-end tests. So end-to-end tests, if you think of unit tests as testing the smallest unit of a code, end-to-end tests test the largest unit of a code. So they're testing a code's ability to perform its intended functions from end to end, from beginning to end. So things to test are that the overall performance and accuracy of the code's main functions, and that the way that users will interact with the code works. So you will, if you're writing a package, there will generally be several different ways that users can interact with your code. So that's why you'll have different types of end-to-end tests. You want to test like if a user is going to interact with it in this way and they want to start with these inputs and at the very end get these outputs, want to make sure that from beginning to end this whole thing works. I also made a note here that this is not always amenable to continuous integration. Continuous integration is a way of automatically triggering tests, your like test set to run. So end-to-end tests sometimes take a long time. In Orbitize, like for example, running your code from start to finish can sometimes take hours or even days. So we don't have all of our end-to-end tests automatically run every time someone makes a change to our code, for example. But it's still important to have them. So here's an example of an end-to-end test that we actually do have in our test framework because it happens to run pretty quickly. So let me walk you through this test. Again, it starts with test underscore, so that means it's going to be automatically indexed and then run by PyTest. We're going to test here that OFT, which is an algorithm, produces statistically comparable output to an independent implementation. So what that means is that we're running Orbitize using a particular algorithm or a particular choice of like configuration of how people might use Orbitize. And we're going to compare those outputs to a completely separate implementation of that algorithm. So we're testing that the overall answer that our code gets is comparable to an independent implementation's answer. So going through, here's where we initialize our main Orbitize object. You don't need to worry too much about what this is doing. And then this is where we run Orbitize. So these first three commands just set up and run Orbitize. Orbits is the output that we get. Here we're just indexing some of the outputs. So we're looking for, in this case, three particular orbital parameters. We're looking for three like subsets of our output. And then we're going to compare against expected values. So this is the expectation for the first output. This is the expectation for the second output. And this is the expectation for the third output. And then the last part is very similar to what our unit test before. We're using pytest.approx again to account for differences in machine precision and here just noise as well, random noise. And then we're going to use assert statements to make sure that the expectations are consistent with what the code actually produced. In this case, machine precision, like I sort of alluded to, isn't the only thing that we're needing to worry about. We're dealing with random sampling here. So there might be some random errors, but some random differences between our outputs and the independent implementations outputs. So here our absolute error tolerance is pretty high. We're just testing that the values that we expect are within 20% of what we think it should be. All right, so time for next Piazza question. What's an example of an end-to-end test relevant for your own research? So I'll leave this up and I'll put this back up in a sec, but let me open up the new question. Okay. All right, so take another 3 minutes. Tell me an example of an end-to-end test relevant for your research. And if you're not doing research, an end-to-end test that's relevant for any type of research problem. All right, take another minute. All right, let's check out the answers. So Ray would input a star with a known rotation period. See if your code outputs the same value. Yeah, awesome. Yeah, I like that you also listed some like edge cases for end-to-end tests. Ray, wherever Ray is. Yeah. Nice. Single stars, it goes through an 8-month observing session. Yeah, awesome. Most science areas of the telescope. Yep, awesome. Comparing expected outputs with previous fits. Yep. Yeah, great. There are a lot of examples of like comparing with like other codes outputs, which A, makes a lot of sense because it's the example that I showed, and B, that's a really good example. Yeah, definitely. This is a really like I want to say often, but that's not common. This is a really often example of like, I think a project that our advisors like to assign to us, like translate this ideal code into Python code for me. So yeah, in that case, making sure the outputs are equivalent in both languages. Yeah, this is a really good one too, Steph, just making sure that your code is consistent with itself, like making sure that the output is always identical if you expect it to be identical. That's a really good end-to-end test. Yeah, testing that a simulation is converged. That's awesome. Yeah, I think similar to what Oscar said too, like if you're doing something that has a sort of theoretical basis, you could make sure that the theoretical expectation is consistent with your empirical approximation or expectation. Yeah, awesome. Oh, this is another really good one, Sheila, like using simulations. So this is something we do in Orbitize too. So for real physical systems, we don't always know what the answer should be. And so it's hard to, we can test that our answer is consistent with someone else's error, someone else's answer, but we don't always know like that these are correct. But using simulated data allows you to know what the answer is ahead of time. If you simulate something from a known physical process and test your code's outputs on that, you can test that it's actually producing what you expect it to. Yeah, awesome. There are a lot of these, which is awesome. I think I'm gonna move on in the interest of time, but thank you all so much. And please read through the rest of these on your own time. Nice, great job, y'all. Okay, so now I want you to get a little bit of practice writing end-to-end tests and unit tests for some code you've never seen before. So this is gonna be a 15 plus 10 minute think pair activity. So the way that this is going to work is I'm going to give you 15 minutes to just work on this activity by yourself, and then 10 minutes to discuss with your partner. There's a link here. I'll also paste this link in the Zoom chat. Okay. So all of the instructions should be on this, should be here. the general idea is that I wrote up a class with some code for you, and I want you to think a little bit about how users might interact with this code, think about some possible edge cases are, and then write a couple of unit tests. And if you've got some extra time, you can think about how to make this code better, because it's not perfect implementation of this. So the purpose of this is to practice writing unit tests and end-to-end tests for an existing piece of code that you haven't seen before. The process, as I said before, is you should spend 15 minutes giving it an honest try on your own, and then discuss your solutions with your partner. And the product at the end is that both you and your partner should have filled in the 2 unit tests and the 1 end-to-end test. Your solutions definitely don't need to be the same, and probably won't be. All right, so it's like almost 40 after. So let's take until 55 after to work on your own, and then I'll tell everyone to discuss with your partners. All right, everyone, let's come back together. I think in the interest of time, I won't have individual groups share, but I will post like my solution to this activity later today, so you can check it out. We've been all sitting for a while, so let's take a 10-minute break, and then we'll come back and finish the rest of the testing activity. So we'll come back at 15 minutes after the hour. All right, so we have a little more time in the schedule than I thought we did, so I'm going to take a quick minute to go over the solution that I coded up for this activity. Keep in mind, this is just one solution. This is not the best solution. Let me share my screen. I'll also post this later, so you all will get to see it. Let me make it a little bigger. Okay, so up at the top here is the same code that you've seen, this compare fitter object or class. So some examples of how a user might interact with the code that I came up with were maybe just fitting a line or just fitting a quadratic function, and then also doing the full comparison of like which one is better, the linear or the quadratic fit, and then plotting the best fit. Some edge cases that I thought of were like 0 data points, so an array of length 0, only 1 data point in your set of data that you're trying to fit a line or quadratic fit to. Another edge case is all data points are 0. Data points perfectly define a vertical line. Maybe you have nans in your input data. There's a lot more. I'm sure you all came up with many more than this. Okay, so here's the first unit test that I came up with, testing the fit line function. So this tests the least squares fit behavior of compare fitter.fitLine, this method. And the test that I decided to go with was checking that the fitted values of M and B, as well as the residuals, are what we expect for a perfectly linear data set. So if there's no randomness in this data, the points are perfectly define a line, I want to make sure that we get the results that we expect. So first I make a time series to test on, define M and B, define some times, and then define the data points. Step 2, I instantiate or create an instance of or an example of this class, compare fitter, with the inputs times and data. Then I'm going to run compare fitter.fitLine and compare to my expectation. So I run compare fitter myfitter.fitLine. Then the way that this code works is that when you run fitLine, it assigns these variables or attributes self.lincoeps and self.linearResids. So now those are set in myfitter.lincoeps. So I can check that the fitted slope and fitted intercept are approximately equal to what I expect. And then I also assert that the linear residuals that I get are approximately equal to 0, because in this case, we expect that these data points perfectly define a line that the best fit perfectly threads through each data point. So for the second unit test, I think that I would imagine that a lot of you ended up testing the behavior of the quadratic fitter. Just to show you a little bit more like other examples of types of unit tests, I wrote a different unit test So I'm testing it on a particular edge case of an empty input array. So this expects a type error by numpy.polyfit. So basically the numpy function that I'm using returns an error when you put in this input. So it's not defined on this input. So I'm testing that we're catching the error as expected. This is another common function of unit tests to catch that to check that you're catching errors as expected. So this is the way that this looks like. I put in the expected empty data set, and then I'm using a try except statement. So I try doing this. I try running the fit line method. What it should do is produce an error. So in this case, it's kind of counterintuitive because if my code produces an error, that means that the unit test passed. So how do you get the test to pass if you caught an error? And that's how you use these try except statements. So if the code does throw this type error, it'll go into this except clause, and you can do whatever you want to do there. You can just print out, I caught the error as expected. Good practice with these try except statements is you can just do, the code will run if you just do try except, and then any error will enter this except statement. It's best practice to catch the particular type of error. So in this case, it's a type error. There are also there are import errors, tons of other different types of errors. So it's good practice to know which type of error you're expecting and catch that particular type of error. Okay, and then the end-to-end test that I ended up coding up was testing the overall behavior for noisy quadratic data. So this is a sort of very realistic example of a way that a user might interact with this code. And I also noted here that this test requires manual inspection of results. So this might not be something that I put in my automated test suite. This might be something that I distribute with the package, but say, users can run this to learn how this works, or I'll run it every couple of months to just make sure that everything's working as expected. So I'm defining some data parameters, generating some noisy data, and then running all of the functions following the workflow that a user might use. So I instantiate a compare fitter object, I fit a line, I fit a quadratic, and I plot the best. And so this is what that looks like. And I might look at that and say, okay, that looks pretty good. I also figured I'd go over this sort of optional activity at the end, with particularly how users might break the code and how you could design it to decrease the probability of breakage. One thing that I thought of is that it might be good to add a descriptive error message for the empty array case. So if you expect sub-functions that you're calling to throw an error, it can often be helpful to catch those errors yourself and give something more descriptive, because maybe users expect something different than your users might not be familiar with NumPy polyfit. That's sort of invisible to them, or a private attribute. So it's good to tell them in the context of your particular function what a descriptive error message is. I don't think I explained that very well, but keep going. Another couple things that could break the code. So right now the output depends on the state. So that means that the code will break if you don't run fit line and fit quadratic before plot best. So this is sort of a classic error of object-oriented programming. So it would be good to fix this or document it. This is a good example where object-oriented is not necessarily the best choice. I think functional would have been a better a better choice here, because the outputs wouldn't depend on the state of the object. And then another thing that I thought of is that if you're running this many times, you might not want to plot every time. Maybe you want to do this like 1,000 times for lots of different data sets. So you might not want to output a plot every time. So you could add a keyword that toggles plotting on and off, or even separate out the plotting and numerical comparison functionality into different methods. Cool. Anyone else have either comments or questions about the main testing activity or additional improvements that you thought of for the code? Yep, great.
One thing we discussed was that when you call a plot best, there's no return. So you look at it by eye and see what shape it plotted. But it would be helpful if the code returned some indication of whether it chose the line or the quadratic. And so maybe like that would allow some more unit testing of the plot function.
Yeah, definitely. So Ray said that it would be good. The plot best function doesn't return, or I think it doesn't even set any attributes of like which one it chose, or which of the linear or the quadratic, which was the better fit. And so that makes unit testing difficult because you can't like assert that linear was the best one in the case where you expect linear to be the best fit. So it would be good to add something like that. Yeah, awesome. Great idea. Any other thoughts? Yeah.
We actually have one more idea of calling the fit line and fit quadratic functions in the init function. Because as it currently stands, you can't even call plot best until you call both other functions, which a user might not know, or it's just extra steps. But if we're going to use this class and always compare them, we should be calling those in the init. So as soon as the object gets made, it'll have its line and its quadratic data.
Yeah, that's a really good idea. So the idea that Ray came up with, Ray and Alex, right, came up with, was to call the fit quadratic and fit line methods in the inits in the init method, because as they correctly said, users will always want to fit line and fit quadratic in the use case that I've outlined for you. So it's not even worth like leaving the possibility open for users to try to run plot best without having run either of these beforehand. So don't even give them the option, just put it in the init so that it's already always run, and then they can just plot best if they want to or not. Yeah, great idea. That's a good solution to this sort of object-oriented quandary. Yeah, Maria, did you have a question or an example?
So it is something that we define at the beginning of the class, right? But if we define the line and fit quadratic after that, how do we call that?
Yeah, good question. So Maria's question, I think, was just like, how would that look if you define fit quadratic and fit line within the init class, and how would you call everything afterward? So I think I sort of didn't explain that very well. I think what I would actually suggest doing in this point is not like calling those methods themselves, but just moving the code. So I would just like put this, oops, sorry, this isn't the, oh yeah, sorry, I thought it was in the testing fixer. So just like move that there, and then move this here, and then just like get rid of this altogether. So you don't actually have to add any additional function calls, but now whenever you initialize a compare fitter object, it already knows what the linear coefficients and the linear residuals and the quadratic coefficients and residuals are. So you don't have to decide as a user to call those functions. Does that answer your question?
Yeah, so I guess now it's plot, sorry.
Yeah, no, keep going.
So plot best, then we have to, I guess, column now self length collapse and so. Okay, yeah, okay.
Yep.
It makes sense.
Yeah. Awesome. Yeah, great thoughts, y'all. Okay, cool. Let's keep going. That was a nice little object-oriented versus functional side adventure. Here. Okay. So let's keep going with the main lesson. Okay, so a couple of folks asked here during the break, how do you make this automated? And as is the classic refrain in Code Astro, there's a tool for that. There's something that does this automatically for you. I've mentioned it a couple times. It's called PyTest. This is a really helpful Python library for testing. And as I mentioned before, PyTest works by collecting all functions that begin with test underscore and then executing all of them. And then it reports failures and warnings to the user. You all have actually run PyTest before. You did it when you were setting up the Code Astro environment to make sure that that Orbitize was working. So now that you have a lot more experience with testing, let's take a look at what you did again and see what's going on. One sec to open VS Code. For some reason, I have never opened VS Code ahead of time, even though I always try to remember to do it. But I never do.
Luckily, it opens pretty fast.
That is true. Okay, let me share my screen. All right. Can you all see the text? Is that big enough? I'm gonna get it one smaller. Okay, cool. So just to orient you, I'm in the Orbitize repository. I'm going to conda activate an environment where Orbitize is installed. For me, the name of that environment is Python 3.8. Bless you. So I'm in my Orbitize directory, the place where Orbitize is cloned. And then all I'll do is run py.test. So the test session is starting. It's collecting all of the tests. So it's looking for everything that starts with test underscore. It found a file with test underscore tests in test/testofd.py. It's now running these tests. While it runs all of these, I hope these pass. That'll be really embarrassing if they don't pass. While it's testing, I'll just sort of show you what the Orbitize test suite looks like. So we have the structure of our repository is that we've got the overall name is Orbitize, and then all of the source code lives in this Orbitize, the same name Orbitize subdirectory. So that's where all of our like main functions and modules live. We've also got a docs directory, so that's exactly the same as what you all were experimenting with yesterday with Sphinx documentation. And then we have this additional test directory. All of our unit tests are at the like root level of this test directory, and then we've also got some additional end-to-end tests that take a really long time to run. So those aren't automatically being executed. So some of these you've seen before. I showed you them in the presentation. I'll show you what some of the other ones look like. So in each of these files, my computer is really struggling to do Zoom and VS Code. So in these files, we've got a bunch of imports. This is the same as any Python file. You could just call this from the command line as Python name of the file and it would run. But yeah, we've got a bunch of individual functions in here that start with test underscore. And we've got descriptions of what each of these tests are doing. We tend to group related tests together in individual files, but you don't have to. You could just put all of your tests in one file if you wanted to. Okay, I don't think I'm going to let this entire test suite run. Yeah, it doesn't, it seems to be.
One test is not.
Yeah, I don't think we're going to run. Yep. It doesn't usually take that long on my computer. It takes probably like 4 minutes, but I think given that Zoom is also happening. Okay, but that's what it looks like. If it were to finish all the way, it would give you a summary of all the tests that passed, all of the tests that failed, and all of the warnings. Yeah, Alex, you have a
Yes, sorry.
Yeah, sure. So in the test subdirectory, we added an additional subdirectory called end-to-end tests. That's here. And these are just Python files that if you call them, they start like a very long test. The only thing that we've done to make them not like run all the way through is just not start them with test underscore. So that's all you need to do in order to say don't run this. Yeah.
There are ways to use fancy PyTest decorators to
Yeah.
specify when tests are run, but it's a little complicated, so we've heard this more simple.
I noticed you have a bunch of different testing files. What are the best practices for where to put tests and how to break files and whatnot?
Yeah, definitely. So the question was that we have tests in different files. What are the best practices for breaking up different tests in different files? I think in general, like if you have like 10 tests or fewer, it's totally fine to just have them in one file. Like you don't necessarily need different files. Once we have like 87 tests, so it'd be a little overwhelming to have, you know, a file full of 87 tests. So we tested, I think the way that we've broken up most of these is each module, so like each individual Python file has its own corresponding test file. We also have some additional ones, like I think there are more testing files that we have than modules. So if there's like a specific functionality or a specific workflow that we're trying to test, we'll add those as well. Okay, so let me summarize. So breakup by module is a good one. And then also just make sure, it's good practice in general to make your Python files not super, super long because that makes them less readable. So keeping related tests together, modulo, don't make the files too long. Does that answer your question? Cool. Okay, so yeah, that's PyTest. Let me go back to the slides. Okay, so PyTest, that I demonstrated it to you right now, you still have to run it yourself. You still have to decide, okay, I want to run my suite of tests, and I'm going to type py.test and type it. There's also things that you can set up, tools that you can set up that are called continuous integration tools. So continuous integration is a practice where a suite of tests is run automatically each time a code is changed. So you can set this up on GitHub. If you have, like, every time you make a push to the main branch or the development branch or even any branch that you have, it can automatically trigger your PyTest suite to be run. And then it will like log all of the errors or failures or warnings and report back to you. Many free continuous integration services are built based off of PyTest. Not all of them are, but a lot of them are. So it's good practice, in my opinion at least, to build your test suite so that it works using PyTest and so that you can also test it on your own computer using PyTest, and then try to get it set up on a continuous integration service. Best practices for continuous integration are to make sure that your code touches, your tests touch as much of your code as possible. So meaning that like you don't have big chunks of code that aren't run through in the tests. Your continuous integration suite should also not be too long. It shouldn't take like hours and hours to run. Good practice is a couple of minutes. Our Orbitize test suite is getting a little chunky at this point. We should probably listen to my own best practices. On the other hand, though, there are like fun badges that you can get for having code that is like, so this metric is called coverage, like how many lines of your code are touched by your tests. It's not necessarily a good use of time to try to aim for 100% coverage either. You want to make sure that like the main functions of like the main ways that people are using your code are tested. But oftentimes like you don't need to, like getting your coverage over 90% is a much better use of time than like trying to get your code from like, 95% to 100% coverage. Just an opinion. So last year and the year before, this slide was where I advertised the continuous integration package that we used with Orbitize, which is Travis. But over this year, I have gotten more and more frustrated with Travis, and I am no longer recommending it. So this was a particular continuous integration service that we used, but they undid the free part of Travis CI this year. And it is technically still free for academic packages, but you have to email them every time you want new credits, and they give you like a small number of credits at a time. And I keep emailing them and they keep giving me like a crumb of credits, and I go through it in like one day. So, okay, I'll stop complaining, but I'm frustrated with them right now. We don't currently have this continuous integration system set up. So that's why I'm giving you all an assignment to go find a better continuous integration service for us to use and report back. There are a lot out there. Google around and see what you find. Yep.
You say that for continuous integration, it runs the test every time the code changes, but like what constitutes a change that would trigger this?
Yeah, good question. So the question was, what constitutes a change so that continuous integration is actually triggered? Usually that means that you make a commit on GitHub. So like, yeah, the way that we had it set up was that anytime something changes on the main branch of Orbitize on GitHub, a test suite will be triggered. I think another thing is that if someone creates a pull request to main, or I think it was a pull request in general, anytime someone creates a pull request, the test suite is triggered. But there's lots of different ways that you can configure it. Yeah, good question. The other thing I wanted to plug is that there are lots of tools out there to control the environment of your tests. You all already are familiar with one of these, which is Conda environments. So Conda environments allow you to specify like what version of Python you're using, what versions of all of the Python packages you've installed are. But there are, as you've all experienced, there are issues with these as well. They can be frustrating sometimes, and sometimes you want even more control over the environment that your tests are being executed in, or even the environment that your code is being executed in. So I'm not going to go into these in a huge amount of detail. I'm just going to sort of say a couple of these words so that you're aware of them and you know where to start Googling if and when you're interested in these. So Docker is a tool for deploying applications inside these things called containers. People usually say they're lightweight because they take up less space on your computer than full virtual machines, which I'll talk about in a second. So Docker allows you to basically create your own environment of like your own operating system, your own versions of packages that are installed. It's very like, there's not a lot of stuff inside of Docker containers. Generally, they're as empty as possible. But it gives you control over how you build up the environment that you want to run your tests and or your code in. So I talked about virtual machines. You can also use these virtual machines, which are much larger. So these basically build a full operating system rather than like imitating one inside of Docker. There are also continuous integration services that allow you to build your own virtual machines to test applications on different operating systems. So this is really helpful, as the name suggests, for like people who are writing apps, because it's very important that an app works on, you know, an Android phone and iPhone and all that kind of stuff. For astronomy, this is important as well. You want to make sure that your code runs on different types of machines. But I think before you go to testing on App Fair, I would probably suggest starting with Docker. So just to summarize, running inside a Docker container or a virtual machine or one of these continuous integration services that uses virtual machine or Docker means that no matter where you run the code, the environment is exactly the same. It's like creating a little computer inside of your computer where you can control all of the settings so that you know exactly the way that your code should behave. All right, I now want to take, almost done with the lesson part of this. I want to take like 5 minutes to create a class-sourced best practices list for testing. So like I did in some other lesson that I forget which one it was now, we're going to use Stack. So if you're on Zoom, you can just type Stack in the chat. And if you're in person, just raise your hand and I'll add you to the Stack. So I'm going to take notes as you say this. All right, so floor is open. What are some best practices for testing your code? Yep.
Start with the simplest, most obvious case.
Awesome. Yeah, start with the simplest, most obvious case. I'll say cases. Awesome. David?
Yeah, cover as much of your code as you can, but don't try and do 100%.
Yep. Cover as much code as you can. No need to strive. Coverage. Yep. Steph?
As you're writing the code, think about how to test it and in fact, there's even people who advocate writing the tests for the right.
Yeah, awesome. So as you're writing your tests, think about how to structure code. Say, some folks even write tests before writing code. Let's get a couple more.
Test often, but make your test sort of not onerous enough that you can test often.
Awesome. Yeah. Test often. Your tests. Not onerous enough. Nice. Any more folks on Zoom? Come on, y'all, I believe in you. You have things, you're just not saying them.
Make sure you have the test and
Awesome.
Ideas off like other people that have in your code, so like code, I did your code.
Yeah, absolutely. I'll say, I'm going to rephrase that as talk to your users to figure out use cases you might not have thought of. Is that a good summary? Yep.
Make sure you get that edge cases.
Edge cases. Very important. Let's do one more from someone on Zoom. I'm gonna stare menacingly into the camera. All right. Okay, you're off the hook. Awesome, thanks y'all. This is a great list. So I will show you the list that I made too. So my list is very similar to y'all's list. Test as many use cases of your code as possible. Write unit tests and end-to-end tests. Write tests throughout the development process. Like Steph said, a lot of people even advocate for writing tests before you write code. Another thing that Jason tells me a lot is to turn debugging scripts into tests. So every time you fix a bug, take the script that you use to test the bug and find the bug and just add that to your suite of tests. That's why Orbitize has so many tests, because we have so many bugs. So coverage is important up to a point. it's more important to test your code in all the ways your users will apply it than to get 100% test coverage. You can have code that is 100% covered, but not bug-free. So it's more important to think about like why you're writing the test and how people are actually going to use it than to try and just get that number to 100% coverage. And one thing that a lot of people ask me, like, what's the best way to learn a package that you're not familiar with or get involved, writing code for a package that you're interested in? I think the best way is to write tests for the package. The developers will thank you for it. If someone just showed up one day and was like, here's 5 tests for orbitize and use cases that you didn't think of, I would fall on my knees and thank them. It would be the best day of my life. So the developers will be really excited about it. And it's also a really good way to learn about the code. Try to break the code and try to write tests that break the code, and then fix the code, and then turn those scripts into more tests. Appreciate the meme. All right, so now let's take 30 minutes to do some activities. The activities that I'm going to assign for you all today are to write a few unit tests and at least one end-to-end test for your package. I'm going to ask you to write tests using the PyTest framework and run PyTest on your test suite to make sure that everything's working. I encourage you to assign facilitator, driver, and navigator roles and to switch often. And then the product should be that you push the code for your test to your group's GitHub repository. So continue to use the GitHub best practices that you all have been using. You could have one person in your group write end-to-end tests on one branch and one person write unit tests on another branch. Collaborate, whatever works best for you. If you have additional time, you finish early, feel free to get a continuous integration service set up. Feel free to do lots of research and tell me which one I should be using. You could learn more about Docker and get it set up for your packages test suite. I've got a Docker like getting started example here. Okay, so it is 10:52. Wow, that took longer than I thought. Let's go until 20 minutes after the hour, so 11:20 Pacific time. All right, let me open up the breakout rooms.
All right, we're gonna try to get back started now. Share my screen. Oops. All right, so we're gonna talk for the last 30 minutes. We're gonna mainly focus on talking about discrimination in software and anti-discrimination practices that you can apply to your software packages to mitigate these effects. So I just like to caveat with, we try to be somewhat general here, but some of the things we're going to discuss is somewhat US centric, just because that's your instructors are all based in the US, but I think a lot of these apply to probably other cultures as well, but just a caveat. So software engineering can and does contribute to discrimination, such as racism and sexism. So I think it generally is always good to reflect on how you are developing your code and assess in what ways could it be discriminatory. So I'd like to start out with defining something like bias. There's 2 types of bias. One is explicit or conscious bias, where the discriminatory action is intentional and clear and overt. Something similar to the overturning the abortion ruling that's happening right now in the US. Another example of bias is implicit bias or unconscious bias. That's where the discriminatory action is unintentional and the person that's doing it is generally unaware that it's happening. Discrimination in software, you have, so I'd say like the first case, the explicit one, usually those are, very forefront, very mainstream, but are probably more rare in occurrence compared to the implicit bias, which happens quite often all the time. Discrimination in software engineering is more prevalent. It's quite prevalent. One of the biggest things is just the demographics of who is a software engineer. So here at the bottom here, this is the 2020 Google annual diversity report showing Google's workforce representation. And this is broken down by ethnicity. You can see that about 50% of Google's workforce is white, 41% is Asian, and all the other ethnicities are represented by just a few percent. And this is not reflective of the US population. On the left, there's also the breakdown by gender. You can see it's 68% men and 32% women. Again, not the 50-50 that we have here in the United States. I won't go into all of these in detail, but there's you can actually, these are all links to various articles or videos about some of these topics. If you want to basically learn more about some of these things that are happening. You can read this article about sexism in hiring, promotion, and pay in software engineering. You can see basically this use of this term culture fit as a way to discriminate on how they hire folks in software. It's not just the who's being hired and who's not being hired. That's a discriminatory practice in software. Software itself is not unbiased. Oftentimes you hear that software is just math, is just algorithms. How could that be biased? But a lot of times these algorithms work on these algorithms don't live in a vacuum. They work with data, and especially many of these data sets are very much very much biased. So on the bottom here, there's kind of two examples. On the bottom left, Twitter in the past used to have this auto crop feature where it would pick out, quote unquote, the most interesting part of a picture and crop to that when the picture is kind of doesn't fit the Twitter aspect ratio. So here on the right, here's two images of Lenny and Carl, popular Simpsons characters, if you recognize them. And you can see in this image, the image on the left, Carl's on the top and Lenny's on the bottom. And the image on the right, Lenny's on the top and Carl's at the bottom. And in both images, you can see that Twitter Twitter automatically cropped the image to the more light-skinned person as they think this is the more interesting part of the image. And you can see how this can contribute to biases. Just even though these are just algorithms and things like that, these algorithms have consequences. It's not just machine learning. On the right, this is this Google image search. One of our previous Code Astro TAs, Mia, she just typed in the word girl into Google image search, and that's what you get as kind of the images you get as the representative images of girl from Google Images. So again, just because you've written an algorithm and it's good for some things doesn't mean that it's not discriminatory, and it's always good to kind of reflect on these things. You can see learn more about some of these consequences, such as facial recognition software working best on white people and oftentimes misidentifies Black people. There's been a lot of I guess activity recently and a lot of money put into these prediction algorithms where they try to use police data to predict crime to see where they should station police and things like that. And oftentimes they just use the existing data, but existing data is already based on discriminatory patterns. It just kind of reinforces those patterns and you get the circular feedback loop. So yeah, I encourage you to open up this slide and click through or watch click through and read these videos or watch these, read these articles or watch these videos to learn more about some of these things. So just like to take a quick minute. So this thing's been really popular recently, this new machine learning algorithm that if you pass it in some prompt, it'll give you some images. It's called DALL-E Mini. You can Google search it yourself and try it out. So I've put in some things that are relevant to me. So here's on the left, I put in, it's a little bit hard to read, but I typed in astronomers at a conference. In the middle, because I recently got married, I just put a wedding ceremony. And on the right, I put impressionist portrait of software developers because thought that was something that maybe you should try to do. So, take a look at these images and think about what sort of biases you see. Maybe take 30 seconds and people have any thoughts about any biases they see, feel free to put them into the Zoom chat or raise your hand.
Those are all guys.
That's right. All the impressionist portraits of software developers are all dudes. Anything else? What do people see? Yeah, a minute.
Only white people that man.
Yeah, there's a lot of white people as like in these images, and not representative of the demographics of the world. Like on Zoom, we got wedding ceremony is very Western centric, is very much indeed. Got more everybody is white. Beards for engineers. I love it. Yes, heterosexual and Western, especially for the wedding ceremony. All suited and bearded on the right. That's very true. Yeah, so I think you guys hit all the things I wanted to say. There was also, if you try to Google like photo of astronomer, or not Google, you put in photo of astronomer into DALL-E Mini, you just get a bunch of pictures of telescopes. So I think that all astronomers are telescopes. Yeah. Yeah, it's very true. Like it seems to be reinforced like it's like these outer like the older scholars in this field. So maybe not representative of who we are. RIP early career researchers, dimly lit conference rooms. Yes, some very good ones here. Yes, so this kind of shows you how we can create these tools. They can produce interesting things like impressionist portraits of software developers, but maybe we should also reflect on what are the things they're producing, what are the things they're not producing, and how does that involve it? How does that participate in bias? So a lot of these things, and also software doesn't live in a vacuum. So even if you write a tool, it's like say you develop a tool for facial recognition. Maybe it's not biased. It works on everyone. But those tools can be used in nefarious ways. So even though we're writing cool pieces of software, you got to think about the context in which they are used. So after people wrote all these facial recognition tools and that work really fast and identify hundreds of faces from a single image, police have been using these to basically cross-match these faces against a database of faces that they have, and basically trying to identify demonstrators and arresting them based on pictures that are posted on social media, basically. Be wary of thinking about the consequences of the tools that we write and how they can impact broader society. So a lot of the things I talked about previously are just general software machine learning kind of things. Maybe so you can think about us as astronomers. We maybe aren't working on facial recognition software. We aren't doing like all of these things. Maybe we're working on a much more narrow scope in our code, but there are still things that we can think about. One of the things is don't contribute to an exclusionary culture in software engineering. I think that's a big thing that affects both us as a community in astronomy, but also in software engineering in general. Don't do language hates. Be like, I can't believe you're using IDL for that kind of thing. If it works for them. It's perfectly a fine way to do their science. Don't micromanage other people's code. So like, oh, you see someone using a double for loop or something, you're like, oh, you should be using an iterator for that kind of thing. That just, oftentimes these things are meant with good intentions, but oftentimes make people feel bad. Don't minimize what other people are doing. If you see someone trying to work on something that you've already done before, don't tell them it's trivial to implement this thing. Maybe maybe now it's trivial for you, but you might have taken quite a bit of time to learn in the past also, and that might be their first time doing such a thing. So that's kind of like a couple of things I brainstormed. So maybe let's take a couple of minutes and think about, reflect in your own experiences, what kind of things you've seen, and maybe let's brainstorm some other bullet points here about how to not contribute to an exclusionary culture doing software development. Again, feel free to, for in-person people, raise your hand. People on Zoom, type things in the chat, and we can put them onto this list. Yep.
But I had friends who like an Astro talk.
Mhm.
They were like, oh, this discussion about the lecture like about racism, and she was timing how much the panel was talking. And it ended up being like the men were talking like 66 times, the women were talking like 33 times.
Mhm.
So I think it's like really like keep in mind that like I guess be aware of how much of the conversation that you're picking up relative to other people, and then also I guess it kind of goes back to the implicit bias thing, is like even if you feel like it's a 50-50 conversation, but it's not. I guess it's kind of
Yeah, that's a great point. So the comment for those on Zoom was that someone observed that, you know, at a panel there was I think males took up like 66% of the speaking time and females took up 33. So it was you know, think about don't hog the conversation. Basically, don't hog the conversation and be mindful of the space you are taking. Saving space for others to provide opinions. Thoughts. I think we had one on Zoom on overuse of acronyms, even when they're not necessary. Avoid overuse of acronyms, especially when they may not be necessary. Consider people outside of your experience when developing software. So not everyone has the same software background or took the same path as you to get to their point. Right.
Being considerate when you're working with people from different backgrounds, and just like need to the African
Yes, very true. So we do a lot of collaborations of being considerate of people's different language backgrounds. One over here.
Actually, piggybacking off of that, try not to repeat other people's sentences for them, because sometimes that happens when someone taking a little bit more time to figure out the word that they want to say. Sometimes they might jump to conclusions and start to talk about it.
So like adding like being patience or something like that. Patience. Yeah. For people.
So I would say I have like 1.5 points. The
Okay.
first point is like you consider people with different language and cultural backgrounds.
Mhm.
Because a lot of times, people from different, I guess, ethnicities and different social backgrounds, they have just different ways of communicating their ideas and different ways of reacting to a certain situation, whether it's like when they're putting together or discussing ideas together. And sometimes what's okay in one culture may be offensive in another. So that can create barriers. The other point I had was it was not particularly relevant to software development, but I think it could be. So it was something some of us experienced in the class where our professor like shamed us for using Google a lot, of constants and stuff like that. So I think not hate people for using Google.
Okay, so for people on remote land, we first talked about also respecting people's cultural backgrounds and the consequences, not just language, but also culture, because even if you share the same language, you might not share the same cultural background. And also to not shame people on, say, Googling for things if that's a perfectly fine method that works for them. Also on Zoom, I think there's also one on cutting people off mid-sentence, not acknowledging the contributions to the conversation. So I'm going to add, don't cut people off. Because let's see, acknowledge people's contributions to the conversation. Linda? Mm-hmm. Mm-hmm. Mm-hmm.
And also just like think about how you can
Mm-hmm.
in the evening.
Right. Consider how celebrations, how to inclusively celebrate evenings, alcohol be for everyone. Okay, so this is a lot of good thoughts. I'm sure there's plenty more, but thanks for everyone for taking the time to think about this and think about things that we should try to do or not do when we're developing code. So let's continue. So here's some things I put down for things we can do to at least help some of the implicit bias. One thing you can do is replace discriminatory language in software development. Things like you sometimes hear this programming terms called like master and slave. Often these terms are not very precise, and it's generally just they don't add anything to the conversation, such as using alternate terms like primary, backup, leader, follower, reader, writer. Things like that are usually generally more descriptive and much less discriminatory than using something like master and slave or blacklist, whitelist. You can alternately use something like block or allow lists. Generally, for every one of these, there's something that's better. In particular, I like to in astronomy, we're not free from this. We're not innocent. There's a very popular, very real astronomy package called Source Extractor that's abbreviated as such that you can find that it's written by a senior astronomer, and they refuse to change the name, but other people have referred to it as SE instead of the abbreviation that the main lead developer prefers. This way we can replace the discriminatory language, even if the lead developer of this is someone that's not amenable to change. In general, naming is a big thing. Generally use descriptive and professional variable names. Sometimes you do don't use swear words because code is the face of your software. That's what people see when they look at your code. If you want to be professional in all other aspects, you should be professional in the code that you develop as well. Bad variable names can make people uncomfortable reading through the code. Also, just clear variable names just from an objective standpoint make your code easier to understand. So putting in things like, I'm not using the worst things here, but using stuff like trash or blah, things like that, don't really add to your code. It's just a place filler thing. You can use better variable names. You can nowadays, disk space is cheap. We can have long variable names. It doesn't affect the performance of the code. Make it descriptive. If you really don't have use for a variable that you it has to output something, you really don't want to use it. The Python convention is to put an underscore. Use underscore as this is a unused variable that is just here as a placeholder, basically. In general, just try to think of. Here's some examples of things I use when I there's something I'm not sure exactly what to call it, but I use temporary image or current value or something like that, just to as it's slightly more descriptive than just using something like blah as your variable name. So think about how you code and how you name your variables. Also, try to be inclusive in your software collaborations. So if you're using code from someone else, cite their code package or maybe offer them authorship as helping you contribute to your code package. pay attention whose ideas get noticed and credited. Some people may not get noticed and credited as others, and make sure that you try to credit them. Maintain open and respectful communication with your team members. I think this goes back to some of the avoiding to use some of the discriminatory language and things like that. Value collaboration over being right. So this is like a, technically Python actually does blank kind of thing. Like, do we need to go into that conversation? Whereas like, even if someone's not exactly precise on their language, but add to that conversation rather than trying to correct every minor detail. Iteration is always very important. So, seek feedback in your processes, your norms, your code, what's going right, what's going wrong, talk with other people that you work with, and think about how you can improve your coding environment. And nothing's ever, nothing's ever perfect, and we're always working on improving things. If you're interested in more about like some history of like software development and people who don't get credited in physics, there's a really nice article here in the link about a series of women who made significant computational contributions to the discovering of chaos theory. And there's a cool article about everything they did, but how that all got swept under the rug. Discriminatory behavior in software does exist, and here's some tips on maybe how to redirect that, or how to address it in kind of increasing levels of severity. So oftentimes, sometimes people might make a comment that's like, say someone makes a bad variable name that you feel uncomfortable about. You can ask them to, replace that variable name with something more descriptive. You redirect it into something that's a constructive action to kind of change their attitudes. If someone says, this is trivial, this is so easy to do, you can be like, oh, can you, if you're familiar with this, can you provide me some code snippet that I could help, get me started on this thing? Call out some of these discriminatory actions. Oftentimes people are implicit or unaware, and many times people actually want to do better, but they don't know that they're doing something that's bad. So you feel comfortable, calling that out or pointing it out and mentioning to them to help them improve. On a bigger scale, you can write a code of conduct for your software package. You can explicitly state what's allowed and not allowed. You can also explicitly state what are the consequences for violating a code of conduct, such as if repeated offenses could result in expulsion from the collaboration. If you're interested in learning more about code of conducts for software packages, we wrote one for Orbitize. You can find it at this link. I'm not going to go through it, but it's not a very long document. You can, I think it's like 2 pages. Yeah, about 1.5 pages. You can read through it. It's very similar to the code of conduct of the Code Astro workshop. So yeah, all right. So I'm not going to go super into that. Let's continue. If some egregious discriminatory behavior happens that you feel like needs to be elevated, discriminatory behavior in software development can be treated like any other professional discriminatory behavior. There are resources at your institution or at your workplace that can help you guide you, or there's avenues for reporting these incidences, even if they're caused by people not at your current institution. So just to summarize, here's some best practices for open source development that have some to mitigate discrimination. Use professional and descriptive variable names, write clear contributor guidelines, track and recognize contributors using something like a change log, so you know exactly, so we can see no one is forgotten in terms of what they contributed to the package. For larger packages, draft rules for the developer community, and credit the authors of packages you use in your code. This includes both citations and co-authorship. So that's all we had for this. In the last 3 minutes, I'll just mention that we said there's also an optional parallelism activity. So parallelism isn't exactly required for most software packages, but it's a topic that some people are interested in. I'm not going to go through the activity, but there's a meme here, so let's at least take a second to appreciate the meme. as a person who's done a lot of parallel programming, if you look at my Twitter handle or my GitHub handle, it's a reference to some very niche parallelism programming concept. So my general rule is avoid parallel programming unless it's absolutely necessary. It generally makes your code harder to debug and increases things in complexity. It's only when the runtime is really significantly improved by parallelism should you use parallelized code. In this notebook, I kind of guide you through the basics of how you can parallelize your code in Python. Generally, there's this concept called pools. You can basically make a pool of worker threads and basically give them a bunch of jobs and have them run things. There are other ways to do parallelism in Python, but generally simpler is better. Parallelism is one of these things that every time I do more of it, I find more ways that parallelism breaks things, especially across different operating systems. So that's just my general thoughts on parallelism. It's actually not a bad idea to open up 12 terminals and launch a bunch of code in parallel, nor is it a bad idea to hire a bunch of summer undergrads and have them do the work. It's surprisingly, parallelized code, you think like, oh, let's take a day and write this and it'll be done. It never ends up being that way. But if you're interested in diving more into parallelized code, we have a notebook here. It's on the day 4 GitHub repo. You can walk through it. There's an activity at the end, and I'm happy to answer questions about this more if you're interested. Okay, so that's I think the end of today. So I think hopefully you learned some stuff about software testing, about anti-discriminatory practices, and tomorrow, we're like Sarah said, we're going to have an optional 5th day. Unfortunately, due to the timing, it has to be on Saturday. But tomorrow, we're going to have a career panel talking about like how industry and academia compare. If you're into that, we'll have people with experience in both software engineering and data science. And then afterwards, we're going to have a project show and tell where everyone gets to compare package projects with each other. So hopefully you guys can stay around and do that. Or looking forward to try out a bunch of these packages because they sound like they're going to be pretty cool. All right. Well, thanks everyone for coming to day 4. Had a lovely day today, and hope to see some of you guys tomorrow.